Thank you all for coming, and I appreciate the invitation to get to speak here. It's a real pleasure to get to visit ICTS. So my perspective is as a physicist, and so I wanted to provide some of the physical backgrounds that underpin some of the vortex phenomena that we've seen. Before I get into the bulk of my talk, I just wanted to give a little bit of an outline to give you some sort of idea of how we're going to extract a category from this vortex equations that we've seen already. So the basic picture that I'm going to try to advocate for is that we're going to be considering a quantum field theory in 3 dimensions, very similar to the ones that we saw yesterday with the lumps and the abelian Higgs models. But I'm actually going to be interested in certain supersymmetric extension of the sorts of theories that we saw before. So the background of what's going to be happening in the next few lectures is going to be in the context of 3 dimensions with n equals 4 supersymmetry. And I'll explain what that means when we get there. But the basic idea is we're going to start with this 3-dimensional theory, and we're going to place it on a space-time manifold of the form sigma for a Riemann surface times a real line to make up my 3 directions. I'm going to mostly talk about the non-compact setting. I won't say too much about higher genus surfaces, and the main type of sigma I'm going to be interested in are going to be disks with certain boundary conditions on the outside. But when we place a 3-dimensional quantum field theory on something that's roughly compact, if you put suitable boundary conditions on a disk, it's morally compact. But when we place it on a compact manifold times a real line, what we'll find is an effective theory that's quantum mechanical in nature. So it's a quantum field theory in 1 dimension. And it's going to live on the time axis. And it's not going to be the standard flavor of quantum mechanical theory you might have seen before. Of course, because this is a really 3-dimensional gadget that we're starting with, it's going to have a hugely infinite dimensional target space. And this target space is going to be governed by the low energy physics on sigma. And by low energy physics, I really mean something that will preserve some amount of supersymmetry, also called EPS. And the sort of first step in realizing this connection to vortices is that the BPS equations that govern this low energy physics on sigma are precisely a version of the vortex equations that we've seen before. More precisely, there'll be a sort of hyperkähler version of them, but morally they're going to be vortices that we've seen. Okay, so what does this offer us? Well, we can reframe aspects of 3-dimensional physics in terms of the quantum mechanics. So the first sort of ingredient on this would be a statement about what the state space, this three-dimensional theory, associates to sigma. So what we'll find is that the Hilbert space of the three-dimensional theory, and I'm going to put a superscript up here, SUSY, which means that these are really going to be some low energy states. They're really going to be zero energy states, as we'll see. So the Hilbert space, the three-dimensional theory assigns to the surface sigma, is going to be identified with the space of supersymmetric states of our effective one-dimensional theory. In the same fashion, the local observables in our three-dimensional quantum field theory are going to be some distinguished subset of the local operators in the quantum mechanical theory. It's not going to be all local operators in the quantum mechanical theory. For example, there will be local operators in the quantum mechanical sense that are extended across sigma, but localized at a point in time. Of course, those shouldn't be identified with local operators in 3 dimensions. Instead, we'll have certain modifications of our quantum field theory that are going to be local on sigma, and those will correspond to local operators in 3 dimensions. And then the same thing would be true if we consider observables in this quantum field theory that are extended in the time direction. So we can imagine choosing a point on sigma and looking at observables that extend in the real line. And this will be identified with coupling to other quantum mechanical theories. And the coupling is going to be local on sigma, as in it'll only depend on a single point on sigma. It won't be sort of arbitrary couplings. So with this reframing, what we're going to then do is we're going to do a process called topological twisting, which will turn our 3D n equals 4 theory to a 3D topological quantum field theory. And I'll explain what topological twisting is. We'll see more of it next week as well. So this will give you a little bit of an introduction to that notion. But the real reason why we do this is if we consider line operators, these same things I was talking about over here. If we consider line operators in the 3-dimensional topological quantum field theory, these form a category. So when we do this reframing, our line operators in 3 dimensions after twisting will become some category, and we'll be able to construct this category from a certain manipulation of our quantum mechanical theory of vortices. And then in my last lecture, I hope to focus on the case where sigma is a disk. With a line operator, I'll just generically call it L, at a point 0, and our disk extended in the timeline, and a boundary condition that I'll explain more about on the boundary of the disk. So the picture you should have is that we have a three-dimensional theory living on a solid cylinder. You can imagine that if I take some sort of time slice, this is the disk that I'm talking about here, and I'll place a boundary condition on the outside of the disk, and we'll have a line operator sitting in the middle there. And when we translate this picture into our quantum mechanical story, what we'll end up finding is that in this category of line operators, the space of morphisms between two lines is going to act on this Hilbert space on the disk with our boundary condition and line operator, and will give us a suitably nice linear operator to another Hilbert space associated to the other line. So I guess in this picture, you could imagine that I have some local operator that will join this line operator L prime to line operator L. And we can act on this Hilbert space by colliding it with these local operators on the line. So what does this buy us in practical sense? We can say that this is a map from our line operator, which will be an object in this category, to a certain Hilbert space. So it'll be a functor from the category of line operators to the category of Hilbert spaces or vector spaces. And this construction with a disk and a boundary condition on the outside will give us a representation of this category, which is going to be some generalization of the notion that you're probably familiar with algebra. This is just a higher categorical analog of that phenomenon. And at the end of the day, I hope to relate these Hilbert spaces and the action of local operators in this category on these Hilbert spaces in terms of a mathematical subject known as Springer theory. And that'll be the subject of the last talk. Are there any questions before I get into the meat of it? This is sort of the broad strokes of what I hope to do over the next few lectures. Okay, so then the first thing I want to start with, keep it nice and simple. Supersymmetric quantum mechanics. So the basic setup is we imagine we have a quantum mechanical system. So you can imagine that the data of such a thing is a Hilbert space. And because we're going to be doing things with supersymmetry, we'll need this to be a Z2 graded Hilbert space. So I should be able to write it as the direct sum of an even space that I'll call H plus and an odd space that's called H minus. You can imagine this is the space of bosonic states, and this is the state of fermionic states. So part of the data of this quantum mechanical system is a Z2 graded Hilbert space. And on this Hilbert space, we'll have a distinguished local or linear operator, the Hamiltonian. And this will respect the grading. So it sends the bosonic subspace to the bosonic subspace and the fermionic subspace to fermionic subspace. And this is going to be a self-adjoint operator. The Hamiltonian of our system. So this is the usual quantum mechanics if we want a supersymmetric quantum mechanics, we gotta have more structure. In particular, we're going to imagine that we have two other distinguished local operators. I'm going to call them Q and Q bar. Q bar will be the adjoint of Q. But unlike H, these are going to be fermionic operators. What that means is they'll map the bosonic subspace to the fermionic subspace and vice versa. So unlike the Hamiltonian, which is a bosonic operator, these guys will be fermionic. So this is what supersymmetry does. It takes bosonic things and maps them to fermionic things, and vice versa. But of course, we don't want just arbitrary Q and Q bar. They should satisfy some particular Lie algebra. First, they should be symmetries of our system. Namely, they should commute with the Hamiltonian. So both Q and Q bar will be symmetries of our system. They commute with the Hamiltonian. And the real important relation that they satisfy is that if you take the anti-commutator of Q and Q bar, this is actually equal to the Hamiltonian. So a physicist would call this 1D n equals 2 supersymmetry. It's 2 because we have two fermionic operators. There's another version of the theory where you just have a single Q and Q bracket with itself is the Hamiltonian. But here we have a little bit more structure. We have two of these operators. If you recognize it, you can also see this as SL1/1, but that's not so important. Okay, so if we have a quantum mechanical system with this Hamiltonian and two fermionic operators Q and Q bar, what does that buy for us? Say it again? Well, this is, so one dimension is quantum mechanics. So in higher dimensions, what we'll see is that there's an analogous structure where you have fermionic operators, Q, or some variant of that. And they'll bracket with themselves to give translations in the other directions. So here we only have one direction, time, and Hamiltonians generate the translations along the time axis. So the general structure of supersymmetry is you have some fermionic operators and they anti-commute to give you translations in your theory. So because we only have one translation in one dimension, it's called 1D. Any other questions? Okay, so now let's analyze some of the representation theory of this algebra. We're going to be interested in the unitary representation theory of this algebra. So let's suppose we have a state, and I'm going to use the standard physicist notation of Bras and Ketz. I hope that's okay with you. If it's not, you can talk to me afterwards. We're going to assume that we have some energy eigenstate. Energy eigenstate. So that means if I act on my state psi with the Hamiltonian, this will give us the energy of our state. This is just what it means to be an eigenvector. So the first thing I want to say, the sort of 0th order thing to note, is that Q psi and Q bar psi are also energy eigenstates with energy E. This is just the statement that Q and Q bar were symmetries. I can act on my system and it won't change the energy levels. The first sort of non-trivial statement that you get as a consequence of having these local operators is that the energy is necessarily bounded from below. It's necessarily 0 or greater. Moreover, the energy is equal to 0 if and only if the state psi is annihilated by both Q and Q bar. One would call such a state a BPS state. So let me just prove this really quickly. It'll only be one line. I'm going to assume that the state psi is normalized to 1. So I can cleverly write the energy E as follows. Well, it's E times 1. Okay, I haven't done anything. But I can pull the energy into the raw and ket. The energy E arises by acting with H on our state psi. And now we're going to apply this commutation relation and the fact that Q bar is Q adjoint. So we can write this as psi Q dagger, or I'll just call it Q bar, plus Q bar Q acting on psi. This is just throwing that commutation relation. And then using the fact that Q bar is the adjoint of Q, we can see that this is actually the norm of the state Q bar acting on psi. That's what this first term is, plus the norm of Q acting on psi. And this is necessarily greater than or equal to 0 because it's the sum of squares. And moreover, the energy can only vanish if both of these quantities vanish, namely when Q psi and Q bar psi are 0. Okay, that's great, but we can push it yet further. The second consequence of this algebra acting on my quantum mechanical system is that the 0 energy eigenstates, the subspace of our Hilbert space I'm going to call H sub 0, is actually equal to the cohomology of the operator Q acting on the Hilbert space. Is it safe to assume you know what cohomology means? Does anyone not know what cohomology means? Okay, great. So let me just prove this really quickly. Let's first assume that the energy is not 0. And let's assume that psi is in the kernel of Q. It's Q closed. Well, then using our commutation relations, I can write psi as follows. It's Q acting on Q bar divided by E psi. In particular, what I've written here is the Hamiltonian divided by E. But of course, the Hamiltonian is written as an anti-commutator of Q and Q bar. And our state's killed by Q, so I only really have one term in this anti-commutator. And when I divide by E, I can sort of soak this all together. And in particular, if our state has non-zero energy and it is Q closed, then it is necessarily Q exact. So that says that the cohomology acting on the energy E subspace is the zero vector space if E is bigger than 0. Q is the differential. So my notation is that this is the space that is being acted upon, and this thing is the differential acting upon that space. Okay, well, what about at energy equal to 0? Well, if Q psi is equal to 0, then the first thing to note is that Q bar, well, psi cannot be written as Q bar acting on any psi prime. Okay, so we've seen that our energies are necessarily bounded from below. This is sometimes called a BPS bound or unitarity bound. We've seen that this zero energy subspace has this distinguished feature of being isomorphic to the cohomology of our supercharged Q. And this twisting notion that we'll get to in future lectures is just a generalization of this notion, where we're going to look at a certain cohomology of our three-dimensional quantum field theory, and it too will be localized to zero energy states. So we've seen this nice feature about the spectrum of our Hamiltonian. The first observable that's compatible with supersymmetry that you're usually introduced to, observable, is called the Witten index. So in particular, I'm going to call this thing I, and it's going to be equal to a trace over the positive energy or positive parity part of the Hilbert space, the bosonic sector. And it'll be the difference of that trace with the trace in the fermionic subsector. And this is often written trace over all of the Hilbert space of an operator physicists call -1 to the f, which is called the fermion number operator. And it acts as +1 on the Hilbert space plus and -1 on the minus Hilbert space. So this is a particularly nice observable. We weren't told to give you any exercises, but I'm going to be a little lazy and make you guys do this one. So the exercise is sort of as follows. The first part is to show that the index I is the dimension of the zero energy bosonic state Hilbert space minus the dimension of the zero energy fermionic Hilbert space. In particular, it's actually independent of beta. Morally, this is because we saw here that every state has a fermionic pair or a supersymmetric partner. And so in the higher energy states, H plus and H minus will cancel each other out in this expression. And only at the zero energy states will you have a possible difference. The second part of the exercise is if we have a family of these quantum field theories or quantum mechanical systems. Suppose we have a family of these operators. I'll denote the parameter of the family, lambda. And they're all going to act on the same Hilbert space. We're not changing the Hilbert space. This is sort of imagining that we have some free theory, and these are the couplings of our free theory. Then the index is independent of lambda. There's one small caveat here. We need to assume that the H lambda are always gapped. Namely, there's a discontinuous spectrum that starts at 0. These are the 0 energy states. And then there's a gap to the first excited state. If you have situations where there isn't such a gap, you have weird issues where states don't necessarily need to come in pairs, and you have some issues in showing that this index isn't actually dependent on lambda. But this is a remarkably powerful feature that we'll see in some of the examples later today. Oftentimes, there's a convenient choice of the lambda, maybe like lambda goes to infinity, for example, that is really easy to compute. And consequently, we can compute this index at that very special value of lambda and learn about what our theory looks like at finite values of lambda. The other thing I want to mention with regard to the Witten index is that there's a natural generalization. Suppose we have additional symmetry generators, things that commute with H, that also commute with the Qs. So let's suppose we have some other self-adjoint operators. I'll call them J sub A. A will be an index that enumerates what these guys are. And I'm going to assume that they commute with one another, so they can be simultaneously diagonalized. I also need it to be a symmetry, so they'll commute with the Hamiltonian. And I also want it to be a symmetry of the supersymmetry, namely the bracket of J with Q is 0, and the bracket of J with Q bar is 0. Given such data, we can define what's called a refined Witten index. That's defined as follows. It'll depend on some parameters. I'll denote them the exponential of nu A, where nu A will be a fugacity for these symmetries, if you like that, or a chemical potential, if you like that language. And it'll take the same form as what we saw over there. It'll be a trace over our Hilbert space. We have -1 to the F, e to the minus beta H. And then we'll have e to the minus nu A, J A. Maybe I'll give this a raised index. So what is this doing for us? This also counts supersymmetric ground states. You can show the same way as that exercise that it only depends on H equals 0, the 0 energy states. And what this is doing is it's counting local operators, including their charges with respect to these JAs. So if you see some expression that's like 2e to the minus nu a, what this says is that, or I'll give an example, nu 1. This says that in the zero energy subspace, you're going to have a difference of 2 in the number of bosons of charge 1 and fermions of charge 1. And in the context of vortices, the refined Witten index will be a version of these vortex functions you might see or have seen, which counts in a suitable sense vortices measured by some quantum numbers. Okay, so enough of that abstract nonsense. The last part of today's lecture, I want to dedicate to giving you examples of these phenomena. The first one I'm going to call A-type superquantum mechanics. There's a B-type one that I don't think I'll talk about, but if you're interested in what that looks like or why they're called A and B, I'd be happy to tell you afterwards. But what is this theory? Well, we're going to choose a Riemannian manifold. So it'll be a manifold M with metric G. And I'm going to choose a real valued function, H. And I need to make one technical assumption that this function is Morse. This is tied to that issue of gappedness of our Hamiltonian. What Morse requires is that the critical points of M are isolated. The Hessian of the Morse function at those critical points is non-degenerate. And roughly speaking, what we'll see is that the Hessian controls the mass of our fermions. And so non-degeneracy of Hessian at these critical points implies this gapness that we need. Of course, because of this sort of phenomenon up here, we have a lot of flexibility in choosing what H is. In fact, it is almost totally independent of H. Might as well give you the action for this. This is probably one of the few actions I'll actually write. We have an integral over the timeline. The first part of our expression, I'm going to be one of these coordinatized guys. So if you don't like coordinates, you might want to look away. The first term is the usual sigma model term that governs geodesics on M with metric G. But in addition to that, we're going to have some fermions that I'm going to call psi bar. And then there's a certain connection here. So I need my metric. And then there's going to be an additional term that depends on the curvature. We have the Riemann curvature tensor where I've lowered one of the other index. And there's a 4 Fermi term. It uses the natural anti-symmetry of these indices because these fermions anti-commute with one another. So this expression is non-zero. And then the Morse function shows up here as well. I have the inverse metric pairing with the partial derivatives of H. I guess just to say that this H is called a superpotential. And then, as foretold in the prophecy, we have the Hessian matrix of H that will be a mass term for our fermions. And then I should tell you what this connection is. It's essentially the pullback of the Levi-Civita connection by the map X minus the Christoffel symbol A, B, C, X dot B, psi C. Okay, so this is our classical action that we can hope to quantize. But before, yeah, we will eventually identify psi bar with coordinate 1 forms, but not quite yet. You should think of it really as being valued in the pullback of the cotangent bundle, or sorry, of the tangent bundle, complexified tangent bundle. Namely, we have this map X from the real line to M, and psi A transforms as if it were valued in the tangent bundle. Like you can imagine forming a vector field, for example. Okay, well, I claim that this thing has an action of that supersymmetry algebra I talked about before. So let me write it out for you. The action of Q bar and Q on the bosons XA are going to be equal to psi and psi bar. The action of Q and Q bar on psi bar A, or psi A. Well, if Q is going to square to 0, this thing better act on psi A is 0. And here, it's going to be X dot minus GAB del BH minus a Christoffel and then acting on psi bar, going to take a similar form. Like that. Yeah. Great. That's not a problem. Thank you. Great. So I have this quantum or this classical system. And what do we do with classical systems? We quantize them. So let me give you a brief description of a certain quantization of this classical mechanical system. The standard lore is that if we quantize this classical mechanical system, the Hilbert space looks something like L2 functions on half the variables. So something like X and psi bar, for example, because there's a first order kinetic term with our fermions, half of the functions is choosing psi or psi bar, and I'm going to choose to work with psi bar. And as mentioned earlier, what we're going to actually do is we're going to identify psi bar A with the coordinate differential dxa. And so this Hilbert space is actually more precisely going to be L2 normalizable forms. On our manifold M, where a form which looks like omega A1 AN dxa1 dxan is identified with the same coefficient psi bar A1 up to psi bar A. So this is how we identify states in our Hilbert space with differential forms on our manifold. Okay. Now, how do we quantize those operators Q and Q bar? Well, let's start with the case where we have no superpotential, H equals 0. This is fine so long as M is compact. But what do we see? Well, first, Qx is dx. And Q dx is 0. So we should think of Q as being the de Rham differential acting on differential forms. It's a little bit more subtle, but if you'd like to see afterwards how this works out, Q bar is actually going to act as the co-differential or the adjoint of the de Rham differential. And here I'm using the Hodge inner product so that the pairing of omega and omega prime looks something like an integral over M of omega wedge star omega prime. And of course, the anti-commutator of these two guys is going to be our Hamiltonian, which is going to be identified with the Laplace-Beltrami operator acting on differential forms. So what does this tell us? Well, our space of supersymmetric ground states, H0, well, we saw that this could be identified with the cohomology of our supercharged Q acting on the Hilbert space. But this is the same as the cohomology of the de Rham differential acting on forms on M. And everyone should know that this is the cohomology of our manifold M. So one important feature here is that, well, the cohomology is a topological quantity. It didn't depend on the metric I chose on M. This is one of those instances of factoid exercise 2. We have the family of metrics on M, and the space of supersymmetric ground states is independent of that choice of metric. For the sake of time, I don't think I can say too much about, maybe I'll just save that for next time. But what I will say is that the Witten index that we talked about before is simply the Euler character of the manifold M, another topological invariant. Just briefly, I guess, when H is not equal to 0, what you end up finding is that the superpotential in the presence of such an H should be identified with the de Rham differential plus wedging with the differential of H. And so long as M is compact, then we can consider, or well, first thing is that that this superpotential is necessarily bounded because our manifold is compact. In particular, the operator e to the h, the exponential of h, is a bounded operator from differential forms to themselves. And moreover, q is e to the minus h, or sorry, qh is e to the minus h, q e to the h. In particular, what we find is that the map e to the h is going to give us the following. Because this thing's not vanishing, it's going to be an isomorphism of our vector space. So we find that the Hilbert space of ground states with a superpotential H is isomorphic to the Hilbert space in the absence of superpotential. And of course, this is just the cohomology of M. So again, we see that we have this deformation invariance where it sort of didn't depend on which H we chose when M is compact. But of course, when M is non-compact, we have many issues. And what we find is that the superpotentials H and a small variation away from delta H will result in the same supersymmetric downstates, so long as delta H isn't too big. Namely, we can't alter the behavior at infinity. Sort of most degenerate case would be looking at Rn without a superpotential. What you find is that there's no L2 states. Well, there's no L2 ground states. So you can't have no superpotential on non-compact manifolds. Okay, so I should probably stop there. Next time, I'm going to talk about a gauge theory version of this and a one-dimensional n equals 4 version of this, and then move on to 3 dimensions and relate it to this super quantum mechanics that we've seen here.